We want to build micro-engines for nanosatellites to allow these small satellites to do real science missions. Currently, space exploration missions cost hundreds of millions of dollars, even more. Now, the way to bring the cost down is to send, instead of large satellites, very small satellites, satellites that weigh between 1 and 100 kilos. And these satellites are very exciting for universities because we can build them ourselves for a very reasonable cost. Now, the big limitation is that nanosatellites are stuck in whatever orbit they're put in. And to free them, we need microthrust. We need a very efficient, miniaturized propulsion system. Now, imagine we have a small propulsion system, actually like our prototype here. You can then go to Mars with a satellite this size. You can go to the moon. You can go to asteroids. You can do all sorts of science exploration missions that are today impossible for universities and for many countries because of the high cost. Now here, this prototype of microthrust is actually the real size, and you can see here how it fits into a nanosatellite frame. The total mass of the system is 200 grams, including all the propellant, and with only 100 milliliters of propellant, we can go all the way to the moon in 6 months. Unlike normal rocket engines, which burn fuel and eject hot gases, ion engines emit ions at extremely high speeds. So in our device here, we first have a reservoir. In the reservoir of volume 0.1 liters, we put an ionic liquid, which is a very conductive liquid. The liquid gets fed to the front, where we have an array of chips. Each chip is microfabricated and contains arrays of small capillaries. The liquid comes to the capillary, and using a very high electric field, we extract the ions and send them out at very high speeds, 40,000 kilometers per hour. Now, because we come out at such high speeds, the system is very efficient, and using only this very small volume, we could send such a satellite in 6 months from Earth orbit to lunar orbit. Microthrust was designed to be a very flexible and modular system, and therefore can accomplish many missions. The two that we have in the shortest term are, first of all, one called OLFAR, which was from Dutch radio astronomers. And what they want to do is take small satellites, take them from Earth orbit, and then fly them around the moon in order to do radio astronomy on the far side of the moon. Another, which we're very excited about, is Clean Space 1. Clean Space 1 is a nanosatellite being developed by the EPFL to clean up space debris. Now, to clean space debris, you have to catch it. And microthrust will allow Clean Space 1 to have up to 18,000 kilometers an hour change in speed, thus catching its target and take it down safely to dispose of it. Our final test system will be ready in 1 year, and in 3 to 4 years we hope to fly on Clean Space 1.